Okay, in section 4.6, we're going to look at how to solve exponential equations. Now, an exponential equation is just really any equation with a variable in the exponent. So if you have a variable in the exponent, we'll go ahead and call that an exponential equation. So for example, you could have 3 to the x minus 7 equals 5. You could have 3 to the x squared minus 7x plus 2 equals 17, x minus 9, anything like that where you have the variable in the exponent is an exponential equation. And our big goal in exponential equations is we want to get the variable, whatever it is, out of the exponent and by itself or isolated. So somehow we want to take this variable like this x up here. I want to take that x and somehow I want to get it by itself. X equals something else. Now the good news about exponential equations, there is absolutely nothing new that we have to really show you how to do. We just have to use the stuff that we've done before, log properties and log and exponential form and exponential law. We just have to use those in some different ways, and we'll be able to solve pretty much any exponential equations that we'll see in this course. So just like for log equations, there are a couple different methods that we can do this. The first method is there's only one exponential term. So there's only one term that has an exponent in it. So if you have this one, this is kind of the best case scenario. This is our basic one that most of us did in Algebra 2. We will just get the exponential term by itself. So we'll get whatever has the variable in the exponent by itself. And then we'll simply change to logarithmic form. Once you change to logarithmic form, you will be able to solve the resulting equation. Because remember, if I ever have log of any base of any number with no variables, this is just some number. Some number that our calculator can find, or you could find, if it's a nice number, you can find just with yourself. So let's look at a couple examples. So this says, solve the following: 3 to the x plus 2 minus 1 equals 7. So the first thing we said, there's only one exponential. There's only one term that has a variable in the exponent. So in this case, we want to get that term by itself. So I'll simply just add 1 to both sides. So we have 3 to the x plus 2 equals 8. So from there, we want to turn this to log form. Now, if you recall, if you have b to the x equal y, that is equivalent to x equals log base b of y. So how I'll do this one is whatever is in the exponent is going to go by itself. That's the whole purpose of turning to log. So x plus 2 equals log base 3 of 8. And now to get it by itself, you can simply subtract 2. So x is going to equal log base 3 of 8. That's some number, right? Because those are both numbers, minus 2. So this is our exact answer. So if I wanted to approximate this solution, in Desmos, log base 3 of 8 I found to be 1.89, with some more decimals, but we'll call it that, minus 2. So our solution is going to be approximately negative 0.11. So log base 3 of 8 minus 2 is about negative 0.11. But if you want the exact answer, which is fine, then just keep it as log base 3 of 8 minus 2. So this next one works very similarly. We only have one variable. We only have the single occurrence of y. So I'll try to get it by itself. So I'll start off by subtracting that 1. So I'll get 7. And then one thing that people sometimes try to do is multiply that 3 and 2 together. That is a big no-no, because you have the y as an exponent on just the 2. So the idea is you should divide by 3. So we get 2 to the y equals 7/3. So now what I'll do is I'll go ahead and put it in log form. So remember, the exponent goes by itself. So y equals log base 2 of 7/3. And again, that is a fine answer. If you wanted to figure out what it is, you can put it in Desmos, and I get 1.222 repeating, so we'll just say y is about 1.22. Now the second kind of exponential equation we'll have is one that we've seen before, and that's when you have more than one exponential term, but you can make the bases the same. In this case, we can solve it just by setting the exponents equal. So this is called the exponential law. So if you recall, it said if b to the x equals b to the y, then equivalently x is just equal to y. So if you can get the bases the same, then all you have to do is set them equal. So if you look at these two examples, these are ones that we can do that. So we have 2 to the x plus 3 and 8 to the x minus 1. Well, I can't really change 2 to a power of 8, but I do know 8 is 2 to the third, because 2 times 2 is 4, times another 2 is 8. So 2 to the x plus 3 will equal 2 to the third times x minus 1. So now what we can do is we have the same base. We can cancel those out and just set the exponents equal. So we have x plus 3 equals 3 times x minus 1. And so I'll just solve this. So I'll distribute the 3. So x plus 3 equals 3x minus 3. So I'll take the 1x to the other side, which will give me 2x. And I'll add the 3 to the other side, which will give me 6. Divide by 2, so x is 3. So really nothing different than what we did before when we solved these kind of things. It's only very nice because the bases can be made the same. The problem, and the more difficult problem, becomes when these bases aren't the same. So let's look at one more where we can get the bases the same and use the exponential law. And I would encourage you to always try to do the ones that have more than one exponential term this way first. So we have 1/3 and 9. So I can turn 1/3 to 3 to the negative 1 times x. And I can turn 9 to 3 to the second, parenthesis x squared plus x. So now when I take just the exponents equal, I get negative x equals 2 parenthesis x squared plus x. Now this is a quadratic because we have a square term. So on quadratics, we typically get everything on one side, try to factor. If it doesn't factor, then we would try to do quadratic formula or some other method. So I'll go ahead and distribute the 2. So 2x squared plus 2x. I'll add the x, so I get 0 equals 2x squared plus 3x. Now this is actually a very easy factorization because the only thing I can factor is I can take out an x. So we have x and 2x plus 3. So my two solutions will be x equals 0 from this factor, and this factor equal to 0, I'd subtract 3 and divide by 2, so I get minus 3 over 2. So with the quadratic, I actually ended up with 2 solutions. So those were really nice. You had two exponentials. You can make the bases the same. The problem is when you can't. So if you have more than one exponential term, but you can't get the bases the same, this is a little tricky. So like if I have 9 to the x and 7 to the x minus 1. No way I can make 9 into 7 or 7 into 9 or anything in between. So we'll have to do it a little different way. And the way we have to do this, we actually have to use the properties of logs. Well, the problem is these do not have any logs to start with. These are exponential. But if you recall from section 5, there was a theorem that said if we had m equal n, that was equivalent to log of m equal log of n. Now what we used it for in the last section is we would cancel out the logs and solve the resulting equation. Here, we're instead going to add the logs to both sides. So instead of going this way, we're actually going to start and make it this way, because we really don't have much else to do. So we will take the log of both sides. Then we will bring down the exponents. We'll distribute and gather all terms with an x to one side, factor an x out, and solve for x. The biggest thing I can tell you that to remember, just remember, log of any base of a number is always just some number, okay? It's not a variable, so log of 2, log of 3, ln of 5, those are all just numbers. So let's look at one. And again, this is take it step by step because these are tricky. So the first thing I would try to do is I would try to get the bases the same. Try to make 3 and 5 match. They do not. So I am going to take the log of both sides. Now, you can take any log you want, common log, natural log. Just for simplicity's sake, I will just take the common log, log. You could do log base 2 or whatever you want, but that just seems like more work. So I'm just going to do log of 3 to the x and log of 5 to the x plus 1. Now the benefit of taking the log is now I can bring these exponents out front. So this will become x log of 3, and remember, log of 3 is a number, equals x plus 1 times log of 5. And again, log of 5 is a number. So I want to get all the things with an x on one side and everything without an x on the other side. So what I'll do is I will distribute this log 5. Because I got to get rid of those parentheses. So I have x log 3 equals x log 5 plus log 5. Now there are 2 terms with an x, so my goal is to get those on the same side. So I will subtract x log 5. So we get x log 3 minus x log 5 equals just log 5. So these properties allowed us to get these exponents out of the exponent. So now, its last step says I'm going to factor an x out. These both have an x, so I can factor it out. So I have x log of 3 minus log of 5 equals log of 5. So almost done. These two, log of 3 minus log of 5, now I can use log properties because I have the word log. So this will be log of 3/5, because remember, when you have subtraction of logs, you can write it as a quotient, equals log 5. So my last step will be to divide both sides by log 3/5. And now I have x by itself. So my final answer is x equals log 5 divided by log 3/5. Now, this is obviously some weird irrational number, but really this is the only way we have to go about getting this answer. So when the bases don't match, we obviously have the hardest scenario because we have to kind of go through this whole process. So let's look at one more example that has kind of this same idea where we have the bases that don't match, and thus we have to take the log of both sides to get it to work. So here we have 4 to the x plus 1 equals 3 to the x minus 3. So what I'll go ahead and do is I can't get the bases to match because I have 4 and 3, so I'll go ahead and take the log of both sides. Again, any log is fine. I'll just do common log. So log of 4 to the x plus 1 equals log of 3 to the x minus 3. So the reason I do this is so I can bring the exponent out front. So we have x plus 1 log 4 equals x minus 3 log 3. Again, can't stress this enough. Log 4 and log 3 are just numbers. So just like any number in front of a parenthesis, I can distribute it. So I'll get x log 4 plus log 4 equals x log 3 minus 3 log 3. So now I want to move everything with an x to one side. So I'll subtract x log 3. But now, unlike the other problem, I have this log 4. Well, I want everything that doesn't have an x on the other side. So I'll subtract log 4 to this side. So we end up with x log 4 minus x log 3 equals negative 3 log 3 minus log 4. So I'll factor an x out, and I'll get log 4 minus log 3 equals negative 3 log 3 minus log 4. So now on the left, I can combine those two logs since they're subtracted. So this would be x log of 4 over 3. I could simplify the right side if I wanted. I could also just keep it just like this. I could take the 3 up, factor a negative out. But I can't do the straight subtraction because they both have a negative sign. So x is going to equal negative 3 log 3 minus log 4 divided by log of 4/3. And this is a fine answer. But obviously not a nice, easy answer like when the base is matched. It's obviously something much more sinister. Okay, let's look at some different mixed examples here of how we can do some exponentials. So this first one, you see, only has one base. And so if you recall, when there's only one base, all we have to do is get that one exponential by itself, which it already is, and just simply switch to log form. So this will be x plus 2, which is the exponent, equal to log base 3 of 7. So log base 3 of 7 is some number. So to get x by itself, I'll simply subtract 2. So I'll get log base 3 of 7 minus 2, and that would be my value for x. Of course, we could figure out the approximation to that, or that's a fine answer too. Now the last two problems here you see have two exponentials, one on each side. The idea is, can we get them to be the same base? Now the first one I don't feel very optimistic because it's just 7 and 4. So if the bases don't match, we'll go ahead and we'll take the log of both sides. So this will become log of 4 to the x and log of 7 to the 3x minus 8. And then remember, when we take the log, we can then bring the exponent down. So this will be x log 4 equals 3x minus 8 equals, times log of 7. And log 7 is just a number, so we'll distribute it in. So we'll end up with x log 4 equals 3 log 7 of x, so all that stuff in front of x, minus 8 log 7. And then our goal is going to be to take everything with an x to one side. So that's going to be x log 4 minus 3 log 7x. I might write it as log 7 to the 3rd x, just to get that exponent up front. You can put the x out front, however you want to do it. Equals negative log, I can write this as 7 to the 8th if I wanted, just taking those two exponents up front. So now the idea is we'll take an x out. So we'll have log of 4 minus log of 7 to the 3rd equals negative log of 7 to the 8th. So putting these two together, since they're subtracted, this is going to be log of 4 over 7 to the third. 7 to the third is 343 equals negative log of 7 to the 8th, and they'll just divide out. So x is going to equal negative log of 7 to the 8th all over log of 4 over 343. So really powerful when you do not have the same base, you can take the log and you just use the properties. So let's look at this last one. Now this last one is 343 to the x plus 1 equals 49 to the 7x minus 9. So we can try to get these bases to match. If you didn't notice these bases match, because they actually can, you could take the log of both sides and go that route, but it's just a little more work. And if you notice, they actually can be turned into powers of 7. It makes it a little easier. So 49 is 7 to the second. And from above, remember we said 7 to the third is 343, so 343 is just 7 to the third. So you can make the bases match. So this makes the problem real quick, because you can cancel the bases out and just set the exponents equal. Again, if this wasn't the case, you'd have to take the log and go through the whole process. So 3x plus 3 equals 14x minus 18. I'll get all the x's on one side, so I think I'll subtract 3x here, and I'll add 18 here. So that's going to give me 21 equals 11x. So x is 21 elevenths. So those are some different ways you could solve some exponential equations. If you have questions, please let me know.